In this video, we're going to do a third example problem practicing the use of our equations for constant acceleration motion. This example problem is going to take things up a step, as we're going to see. So here's what's happening. We have a car driving along, and 200 meters in front of the car, there is a peach stand. And the driver of the car would like to buy some peaches. So the driver of the car would like for the car to stop right in front of the peach stand. Now, this is a funny kind of a car. The car can either drive at constant velocity or reduce its speed at a rate of 2.5 meters per second per second. So what we expect is going to happen is that the car is going to continue at a constant velocity, then the driver hits the brakes. And once the driver hits the brakes, the car is going to get slower, hopefully coming to a complete stop right at the peach stand. So part A says, where should the car start braking to stop at the peach stand? Part B is find the total time for the entire process. So we're going to go to our handout again. So step one, draw a clear sketch illustrating the problem. So we have the beginnings of a sketch right there. Step two, draw a coordinate system. So we can use an x-axis, which runs along like so. The coordinate system should have a clearly marked origin. Let's put that origin right at this point right here where the process starts. 3, identify and number the moments of interest. Here, I would invite you to pause the video and see if you can put in the moments of interest, label the moments of interest, and you could even go to step 4 and write in all the symbols we are going to need denoting the various kinematic variables. Then you can rejoin the video. Okay, we have 3 moments of interest. So let's say moment of interest 0 is where the driver sees the peach stand. The next moment of interest will be where the driver starts to brake. So let's call that moment of interest 1. That is where the driver starts to brake. And let's put moment of interest 2 right where the car has hopefully stopped right in front of the peach stand. So this would be moment 2 right here. All right, now we're going to put in our kinematic variables. So at each moment of interest, we're going to have time, position, velocity. So at moment 0, time 0, position 0, velocity 0, moment 1, time 1, position 1, velocity 1, and at moment 2, time 2, position 2, and then velocity 2. Okay, now if we come down here and actually read what it says, for a constant acceleration problem, next to each moment of interest, write down symbols to denote time, position, and velocity. So we write the acceleration off to the side. So we put in all of our time, positions, and velocities. Now I want to put in acceleration. So the idea is that there is one acceleration as the car goes from moment 0 to moment 1. Let's call that A01. And then there is a different acceleration as the car goes from moment 1 to moment 2. Let's call that A12. Okay, so now we get to step 5, which is to fill in the kinematic variables. So for those kinematic variables for which a value is already known, go ahead and put that into the figure. So pause the video, go ahead and fill out what you can fill out. And then when you've given it a go, rejoin the video. All right, so we're going to say that the process starts at time 0. We already decided that the process starts at the origin, in other words, at x equals 0. And the velocity is 0. The velocity, excuse me, is 15 meters per second, that was given. Now, how about the acceleration between moment 0 and moment 1? Well, the car is moving at a constant velocity between moment 0 and moment 1. So if the velocity is constant, then the acceleration would be 0. We can put that in. Now we can come to moment 1. Now, the time at moment 1, not given. The position at moment 1, not given. Now, how about the velocity at moment 1? Well, we know there's a constant velocity all the way from moment 0 to moment 1. So if the velocity at moment 0 is 15 meters per second, it would be the same thing at moment 1. Now, at moment 2, we don't know the time. The position is given, 200 meters. And at moment 2, we hope that the car has stopped, so we put a 0 there. Now, how about the acceleration? Well, remember what we've learned about the direction of the acceleration. If the speed of an object is decreasing, then the acceleration is opposite the motion. So our car is going to the right, but getting slower. That means the acceleration is to the left. Since the acceleration is then in the negative direction, we're going to put in that the acceleration is negative, namely minus 2.50 meters per second squared. Okay, now we come to step 6, which is to write down the equations that we're going to use to solve for the unknowns. Now, what this first part of the question is asking us to solve for is the position where braking starts, namely x1. In order to solve for x1, we're going to need one of the equations here. But since this is our first problem with the 3 moments of interest, let's think a little bit more about what's going on here. These equations apply only when the acceleration is constant. In this problem, we do not have constant acceleration all the way from moment 0 to moment 2. We have constant acceleration from moment 0 to moment 1, and we have constant acceleration from moment 1 to moment 2. So when we apply these equations, we can use them as written to connect moment 0 to moment 1, or we can use them to connect moment 1 to moment 2 by changing the subscripts so that we are connecting 1 to 2. And the way we would do that is changing the zeros to ones and the ones to twos. So try and find an equation where x1 is the only unknown. When you do so, you can consider the equations here as written, connecting 0 to 1, and see if you can find one where x1 is the only unknown. Or you could try the equations not as written, but changed so that they connect 1 to 2, right? You do that by changing the subscripts. So pause the video, give that a shot, and once you've given that a good honest effort, rejoin the video. What we want to do is take these equations and change them so that they connect 1 to 2. And if you do that, you'll find that equation 4 turns into something where x1 is the only unknown. So that's what we're going to do here. We're going to take equation 4, except we're going to rewrite equation 4 so that it connects 1 to 2. And we do that by changing the zeros to ones and the ones to twos. And when I do that, I get v2 squared equals v1 squared plus 2a times x2 minus x1. Since I'm connecting moment 1 to moment 2, I would use acceleration a12. And you can see here x1 is the only unknown. So let's do the algebra and isolate x1. Then after isolating x1, we will make our substitutions along with numerical values. Okay, so v2 is 0, so that can go away. Now we're going to start isolating x1. So take that v1 squared and put it on the left where it picks up a minus sign. And after you do that, you can divide through by 2 times a12. And then what we have is that all of this stuff is equal to x2 minus x1. Okay, now we're going to take the x1, move it to the left, take this whole business and move it to the right. So we're swapping those terms between the two sides. And since both of those terms start out with minus signs, then after we swap sides, both terms will end up with plus signs. So we get then x1 equals x2 plus v1 squared divided by 2a12. All right, now making substitutions, x1 equals 200 meters plus v1, 15 meters per second, all of that squared divided by 2, and then A12 was minus 2.50 meters per second squared. Now punch all of that in your calculator. I believe you will get 155 as the numerical value, but let's do our unit checking. That first term there has units of meters. That's what we would want for a position. Now that second term, we would want that to have units of meters as well. Now, does it? Let's check that up here. So the numerator has units of meters squared over seconds squared. The denominator has units of meters per second squared. Cancel seconds squared. Meters squared over meters is meters. So both terms, in fact, have units of meters. So our answer for part A is 155 meters. Part B, we want to find a total time for the process. Now, the total time for the process will be T2. If we remember the equations, remember that we can only use these equations to connect 0 to 1 or 1 to 2. Again, the reason being that these equations only apply in constant acceleration processes. Okay? So if we try to find time 2, we can only use these equations here to connect time 2 to time 1, but time 1 is unknown. So we have to start out by using the 0 to 1 equations to get time 1. Then, once we have used the 0 to 1 equations to get time 1, then we can use the 1 to 2 equations to get time 2. So I'm going to invite you to pause the video again. But when you pause the video, you're going to first figure out which of these equations can be used to connect 0 to 1 and get time 1. Once you've done that, figure out which of these equations can be used to connect 1 to 2 and then get time 2. Let's get started by solving for time 1. To solve for time 1, we're going to pick one of these equations here, written so as to connect moment 0 to moment 1. And we're going to look for one where time 1 is the only unknown. So the most convenient equation to use here is number 3. So I'm just going to copy number 3 over here, using it to connect moment 0 to moment 1. So I then have x1 equals x0 plus v0 delta t plus 1/2 a delta t squared. Now, the acceleration as we go from moment 0 to moment 1 is 0. So this term goes away. And you may recognize here our kinematic equation for constant velocity motion. Anyways, let me change that delta t to t1 minus t0. Now, x0 was 0. T0 was 0, so I can solve for T1 here, just divide through by V0. And I have then X1 over V0 equals T1, or switching sides, T1 equals X1 over V0. And then substituting, X1 was 155 meters. Divide by V0, which was 15 meters per second. And I get 10.3 seconds. Right? As far as the unit checking, meters cancels meters. 1 over seconds in the denominator flips up to become seconds. Okay, so now we have time 1. And when I get these intermediate values, I like to go back to the figure and put them in. So x1 I should have put in earlier. It's 155 meters. Time 1, 10.3 seconds. Now that we have time 1, we can use this same set of equations connecting moment 1 to moment 2 and try and solve for t2. Now, if you haven't done this already, this would be another opportunity to pause the video and try this on your own. Go through the equations, thinking about the equations connecting moment 1 to moment 2, and see if you can find one where the only unknown is t2. And if you can find one, go ahead and solve for t2. So there are probably different ways to do this. I think the most natural way to do this is to use equation 2 here, but rewriting it so that it connects moment 1 to moment 2. So using equation 2 again, connecting moment 1 to moment 2, it becomes v2 equals v1 plus, then the acceleration becomes a12. And then delta t would be, instead of t1 minus t0, it would be t2 minus t1. Okay, so you'll notice that our only unknown is t2, so we can go ahead and solve for that. v2 is 0. So let's do the algebra. Take v1, move it to the left where it picks up a minus sign. And while we're at it, let's divide by a12. So we get minus v1 over a12 equals t2 minus t1. Now I'm going to take that minus t1, move it to the left where it picks up a plus sign, and then flip sides. So I have t2 equals t1 minus v1 over a12. Okay, substituting, t1 is 10.3 seconds minus v1, 15 meters per second, and then divided by a12 minus 2.5 meters per second squared. I get time 2 equals 16.3 seconds. And there you go. This time I will leave the unit checking as an exercise. Okay, so now we have completed our third of our example problems involving constant accelerations. And this was the first one where we had 3 moments of interest instead of 2.